So on page 352, we're going to take a look at another example of our right-hand Riemann sum calculations. And in this case, we're going to get a little bit more specific and go ahead and use a half-unit interval. So we're going to let these rectangles get even smaller in this example. So we're still using the same upside-down parabola and the same interval from 1 to 7. This time, though, we're going to count by a half to get our base length on each rectangle. So from 1 to 1.5 would be my first rectangle. I'm going to trace up on the right-hand side because we want a right-handed point. And I'll go to the left and then back down to create my first rectangle. So if I repeat the process, this time I'm going to go from 1.5 to 2. I'll trace up the right-hand side, make my dot, go to the left, and then back down. So I'm just going to go ahead and through here, go ahead, draw all these rectangles in, and then we'll take the time to go ahead and calculate the area of each one and add them together. Alright, so it looks like we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 rectangles. So we have to make sure that in our calculation we actually have 12 individual areas that are going to be represented here. So if we take a look at what we have to do to calculate the area, we're going to write an integral from 1 to 7 of the function f of x dx. And this is about, we're going to have to do the sum of each individual rectangle. So the base of my first rectangle is a half, and then the height is going to come from the right-handed point that we drew on the curve itself. And this point is on the curve at the x value of 1.5. So I'm going to go ahead and plug in 1.5 into my function to figure out what that height is. For the next rectangle, it's going to have another base of a half, and this time the right endpoint had an x value of 2. Alright, so I'll have f of 2. And I'm just going to keep adding every single rectangle all the way through. It looks like my last right-handed point comes from the x value of 7. So I'm eventually going to have to plug that one in. So it looks like we have a pattern of 1.5, 2, 2.5, 3, 3.5, 4, all the way up to 7. And since we've done previous examples of this right-handed Riemann sum example, we already know what the whole numbered values are for f. You might have to, however, take the time to calculate f of 1.5, f of 2.5, f of 3.5. So I'm pretty sure you can use your calculator to help you do that. Just in the end, make sure you can get something around 38.917. Alright, now if we try to think about if this is an over or an underestimate, we have to take a look at how we drew the rectangles, and hopefully we drew them as accurate as possible. Remember, this area is supposed to represent the area under the curve, and when you're drawing in rectangles, sometimes you're using area that was outside the curve, or maybe you're not including as much area as you actually should be. For instance, these first few rectangles I drew, I actually am counting outside area that I should not be, but these last few rectangles here were not large enough because I still have some area that should be accounted for but wasn't. So we kind of have to weigh our options here. Do we have more overestimate or underestimate in the case? And just because visually it looks like these underestimates are more than those little overestimates, I'm going to say that this is an underestimate, okay, as an educated guess. And hopefully by this point we're starting to see kind of how we start to be a little bit more accurate in terms of this area value, because notice how compared to some of the other examples, this over area or under area is starting to get much smaller than what we've seen in the past. So we could probably make an inference or conclusion in this case. We can say the area approximation becomes more accurate when the lengths of the rectangles decrease. Basically saying how the length of each one, okay, or maybe the width on the bottom, depending on the wording you want to use. How the rectangles are getting thinner in size. Notice how we're getting more accurate because we have less over or under values there. So graphically, why do you suppose this is true? Just like how I said, you're getting less over values and under values. So the thinner rectangles are creating less over / under estimate errors. Okay, so this was less error than we've seen in previous examples.